Okay, so this bloody HP has been giving me nightmares, and I have wasted half an hour trying to figure out what happened. Every time I update the operating system, it goes bonkers on me with this software called Panopto that I'm using for recording. Anyways, so this chapter 5, is going to look more closely at climate change over the last 135,000 years, which is essentially the last glacial maximum. So Homo sapiens arrived around 200,000 years by all the evidences we have, and there have been several climate change signals along the way before we got into the glaciation. So we will see the idea of marine isotope stages, which are cooling and warming episodes of order a millennium within the long-term glaciation periods that we look at. Okay, so here we let's start with something we already saw. So this is from the International Ocean Drilling Program, which is a modified version of results from various papers that also combine the future projections here. So average global surface temperature difference compared to 1961 to 1990 baseline. We've already looked at going back to the time of the dinosaurs, the Paleocene, Eocene thermal maximum, the hothouse we had, and then the long-term cooling with kind of a pause here. We talked about the rise of the Himalayas, Andes, a drawdown of CO2, and the last glacial maximum, and coming out of the glaciation into the Industrial Revolution, modern warming period, and where we may be headed according to the IPCC scenarios. So we've already also mentioned the scale changes in the signals that are recorded in here, going from higher frequency precession and obliquity timescales into the Pleistocene, which you cannot see clearly here, where we had 100,000 year timescale, and that timescale is seen more clearly here. And this figure puts together the temperature signal in red and the associated CO2 signal in blue. And what the point of this figure particularly is that this data from Vostok Ice Core shows that temperature signal led the CO2 signal. So during natural variations, climate variability during this time before the human activities and global warming, orbital forcings, which we will look at in this chapter, initiated or terminated glaciations, and there was a corresponding response in covering of the ocean, of land, vegetation changes, ocean carbon cycle changes, and so on. So the temperature change initiated by the orbital forcing appears first, and then you are followed up with CO2 changes, whereas in the present, since Industrial Revolution, what we are doing is we are increasing CO2 much more rapidly by fossil fuel consumption, land use change, and so on, and temperature is trying to follow. So it hasn't followed yet with the same kind of sensitivity, climate sensitivity that we see here. Okay, so we will look at some of the feedbacks and try to explain why these warming phases. So remember, you're going here, time going this way. So let's say you're starting at a glacial maximum somewhere here, coldest, and then the warming phase is very rapid. The next cooling phase is slow, over 100,000 year time scale, rapid warming, and so on and so forth. So these are the internal feedbacks. The best way to think about it is that sun comes up in the morning, sun sets in the evening, unless you're in the polar circle, and sun goes north and south. There are seasonal changes, and yet weather can change multiple times during the day because there are feedbacks in the system. The sun's energy is taken to evaporate, to create clouds, to create winds, temperature gradients, pressure gradients, and you get internal feedbacks which create multiple time scales which are not completely synchronous with the changes in solar radiation forcing on modern timescales, just the diurnal cycle and seasonal cycle, because ocean stores the heat and releases it, glaciers melt, glaciers form, albedo changes, and so on and so forth. So here orbital forcing changes introduce onset of the glaciation or the termination of the glacial period, and you get these timescales which are not necessarily directly related to the timescale in the forcing. So looking at those timescales, then Milankovitch cycles, because Milutin Milankovitch was the first one who put a mathematical formulation before on these orbital forcings, but James Kroll had done the work before him as well. So eccentricity change is basically how the orbit of the Earth around the Sun changes. The change is small, only 0.02% or I think of the ellipticity. So the change in energy received from on Earth because of the distance changing is not very significant. But what happens is that timescale forcing combines with the so-called precession, because Earth is orbiting around its own axis and going around the Sun. It wobbles. You can see it's pointing to North Star Polaris now. At some point at these time scales of 26 kilo years, 26,000 years, it would point to Vega, for example. So it's like a top that wobbles when it slows down. We'll see in a minute that there is also a wobbling of the orbit itself because of the pull from other planets. Which means the time when summer solstice, winter solstice, and the equinoxes happen change as the orbit changes. So that's called the apsidal precession. So those can combine with the ellipticity to create stronger forcing, which are manifest in the records that we look at here. Okay, and there is an obliquity forcing where the tilt of the Earth's orbit, Earth to the orbital plane changes from 22.5 degrees to 24.5 degrees. Right now we are at about 23.5 degrees. This happens on a 41,000 year time scale. So based on these various forcings, either the seasonal contrast between the hemispheres changes, because here the total energy received doesn't change, but the angle at which the summer hemisphere faces the sun or the winter hemisphere faces away from the sun changes. So you change the distribution of energy, seasonal contrast, and this also changes just the distribution of energy and not the total energy, as opposed to this, which will change the amount of energy received because the distance changes and the energy drops off as 1 hour r squared, as you know. So here we are looking at the apsidal precession. So if you go back to 16,725 years, let's start here. Today we have winter and summer solstices at December 21st and June 21st, and we have equinoxes at in March and September. 5,750 years from now, you would flip these things around and you will have solstice happening in March and September, and equinoxes happening in June and December, unless of course you adjust the calendar, which is what will end up happening. And 11,500 years from now you will flip it back from there to there, but now you're here and here, so December is here, June is here. As you know, now we are closer to the sun by a little bit during December, January than during July, August, which means the boreal summer is milder than it could be if it was closer by a little bit, and similarly winter could be harsher by a little bit. So 16,725 years, you will flip back again like this. So this is the apsidal precession. We are going in this direction. And this is something to keep in mind as well. So Milankovitch cycles then showing precession, eccentricity, and obliquity cycles were the last 140,000 years, which will be the focus of this chapter, but we will go through how we determine these changes Milutin-Milankovitch calculations, orbital parameters are mathematically simple and can be done. So this kind of calculation is easy. But the impact of that, what kind of feedbacks are triggered, what are the multiple timescales that are created, depend on intricate feedbacks in the system, which is what we will look at. So here is the precessional forcing, eccentricity, and obliquity. So you can see the different timescales. This is modulated. Unlike this, looks more uniform than here, for example, and this one is a much slower time scale. So this is modulated by eccentricity. So those two combine to give us a rich spectrum of time scales that we keep looking at. Along the way, solar insolation changes as well. So we are looking at solar insolation over the past 120,000 years for January and July at 65 north respectively in watts per meter squared. These solar insolation parameters were used in a 122,000 year time series climate simulation performed by UVic Earth System climate model. We will come back to that. UVic is University of Victoria, which has a simple Earth system model, which we will define what it means. But you can see that in January and July, we look at 65 north because that's kind of a critical latitude where radiation forcing changes can initiate or terminate glaciations. Okay, basically glaciation is where snow falling in one year doesn't melt through the summer. More snow falls on top and can get compressed and begin to build a glacier, or melting of the glacier can be initiated by radiation changes, and albedo changes will then keep driving it, and glacier can almost disappear. So those are the kind of feedbacks that we will look at. So let me stop this introduction here, and we'll keep going into more details of the various climate feedbacks we need to consider, various proxies used to reconstruct the past climates, and the climate models used to reconstruct the past details that are not easily inferable just from data. And the same models can also be used for the future in terms of projections that we just looked at as to how much warming may happen in the future if we continue our emissions, and what are the different pathways we can take in terms of emissions, renewables, technologies, policies, etc., to change the future trajectory of warming to remain safe. For example, you might have heard of the 1.5 degree warming target, 2 degrees C warming target by 2100, and so on. So how do we plan to stay below that? So models are used also to do those kinds of calculations. So we will introduce the models very briefly. I have a whole course on introduction to climate modeling and proxies, podcasts, and so on that you can look up. But here we are going to focus on climate change over this period of 135,000 years, mostly focusing on potential drivers of human migrations and other evolutions, behavioral, anatomical changes, developmental changes, and so on. Okay, so let's leave this here.